In this video, I am going to show you how to build a linear regression model using SAS. I'll take a data set to show you how to build a model. The data set that I'm going to take is height weight, which has got four variables: sex, the age, height, and weight. So we have data for sex, age, height, and weight for each individual. So we will try to build a model which will find out the weight of an individual given his sex, age, and height. Okay, so I'll first run the data statement in order to create a SAS data. So the data is STWT, which stands for the height and weight. All right. Once the data is ready, the first thing that we will do is we'll do a simple exploratory data analysis. In exploratory data analysis, we try to understand the nature of the data before starting to build a regression model. We'll first see what is there in the data. To do so, we'll use the proc content in order to find out the details of the data. So we'll use proc content data HTWT, which is the name of the data set, run. Okay. Now in the output you can see the details about the data. So there are 22 observations in the data. There are 4 variables, and there are also other information related to the data which is given. But we are more concerned about the number of variables, the number of observations, and so on. We have got 4 variables: age, height, sex, and weight. The type of the variables are also given, and also the length is given. All right. So we'll first try to get the summary statistics of all the variables. Okay, so to do that, we'll use proc means data and then name of the data set. We'll run proc means first. All right, so there are 4 variables. The first one is sex, which is an ordinal variable. I'm sorry, which is a categorical variable, and the categories are M and F, which are characters, right? That's why we cannot get a summary statistics of sex. But other 3 variables are the numerical variables: age, height, and weight. All 3 are numerical in nature. Hence, we can get the mean, standard deviation, and minimum, maximum, and so on. So we've got the mean of age, the mean of height, and the mean of weight. We'll also get the standard deviation of that, the minimum value, and the maximum value. The reason why we would like to understand the summary statistic of the data or the variables before going for building the model is that we'll get to know if the data is good enough or not. So what are the information that we can get from the summary statistic? Well, for any variable that should be used in a model, in a regression model, it has to have a non-zero standard deviation. Standard deviation cannot be 0. Now in all 3 cases we can see the standard deviation is greater than 0, and that's a good thing. A standard deviation 0 or close to 0 is not an ideal variable for its use in linear regression. So what it essentially means is that there is no variation in the variables. It's just a constant, and that is not a good variable for the model. You can also get to know the extreme values in variables which can cause problems in linear regression. So what do you mean by extreme values? So anything that is just too low or too high, so that could be a problem. Now defining too low or too high is a very difficult thing, but if you are concerned with a particular area and you know what is what is considered to be an extreme value, you'll be better be able to understand which values can be defined as extreme values. And remember that extreme values should be removed from your data before you go for building a linear regression model, because it's going to give a wrong result or bad result or inefficient result, so to say. So in our data we don't see any issue, except there are few outliers, but we won't remove them because they are not too many. Okay, I've just checked the data before this particular session, so the data is more or less fine, so we can go ahead with modeling. And in case we find some issue while building the model, we can come back and we remove. So we can you can also remove this data, bad data, or extreme values at the time of building model. So just that you have to keep it in mind. All right. As I've said, sex is the one of the categorical variable that we have, and then they've got two categories, male and female. So we'll like to know how many are the male and how many are female in your data set. So for that we'll use a proc frequency data, and what we have found here is that there are 16 females and there are 5 males, and one data point is unknown as to whether it is a male or female. So that is one is unidentified one, and the other 21 observations are identified as male or female. 5 of them are male and 16 of them are female in nature. So 72% of the data is female and 22% of the data is male. This is important to understand the distribution of data across different categories, because if there is a huge difference in the percentage of categories, then you might want to have separate models. You may not have just one model which will be okay for male and female, given the fact that there is a significant difference in the percentage of the presence in the data set. And that's what technically known as segmentation. So you can have two segments of model, one for male population and the other one for female populations. So if they're very close by, let's say they are like 45% and 55%, which difference is not very significant, in that case you may go ahead with just a single model. Whereas if there is a significant difference, you may consider to have separate models. All right. It's also important to know how many of the observations are missing in nature. So it's important to know that, and I'll tell you why it is important, because missing observations are deleted from the data at the time of running your regression model. So this is this is something, a feature of your software. SAS deletes the entire row that corresponds to the missing observation. We have got one missing observation in this case, so out of 22 observations we'll just be missing out on one observation, which will be deleted at the time of running your regression. So at this point of time, you should think about whether you would be fine with this particular deletion thing, or you will replace this missing value with some kind of a missing imputation. So what people normally do is that they assign some value to this missing observation. It could be standard deviation or mean. It could be mean of the a particular variable which is missing out. But in this case, the gender of or the sex of the particular individual is missing, so we cannot use mean or something like that. Okay, so it is up to you if you're okay with the missing observation to be deleted, or you want to replace it with a suitable value. If the percentage is very less, then you may think of just be okay with the deletion thing. Else, if the percentage of missing observations is very high, then you probably have to impute the missing observations. All right. The next step in building a model is estimation. Uh, so we, so you're sure about your data now. You understand the distribution of the data. You understand the segments that you will be having in your data, and the next step is estimation. As you know, if you understand a linear regression is nothing but is a linear equation, so to say. In linear regression, you have got a dependent variable and you have got a bunch of independent variable, right? So if you're not familiar with the theory of linear regression, I suggest you to go through the theory first. You can find a video about the theory of linear regression in my channel, and you can also find it in other sources in YouTube or in Google. Just to give you a brief background of what a linear regression is. So in linear regression, we have got we try to find the relationship between a dependent variable with a bunch of independent variable. Okay, so for instance, let's say x is an independent variable and y is a dependent variable. So we try to predict the value of y based on the value of x. In order to do so, we try to regress y versus x, and in while doing the regression, we find out the estimates known as a and b. Now using a and b, we can write an equation like this: y equal to a plus b x, right? So given the value of x, we'll be able to find the value of y. Okay, so normally people use y hat and x hat to denote the variables as estimated variables. So these are estimated from the data. So there is just a slight difference in the notation. So what we're trying to find here is predict the value of your dependent variable. So y is the dependent variable here, given the independent variable. Okay, and independent variable could be one variable or could be a number of variables. Okay, x is your independent variable. You can have a number of independent variables. Okay, the total number of estimates that you're going to have is just n plus 1. So n is the number of independent variable. So the first one is called intercept, and the coefficients or the estimates which are associated with each independent variable is known as slope coefficient. Okay, so this is the basic this is just a basic background of what a linear regression is. And how do we interpret this linear regression? We'll see that once we have the regression equations in place. All right, so how do we write a linear regression syntax in SAS? We use proc-reg. So regs stand for regression. So this is a inbuilt procedure in SAS that can be used to do the estimation. Proc-reg data, the input data set, and then you define a model. The model is weight equal to height and age. In left hand side of the equation, you have got the dependent variable. In the right hand side, you have the independent variable. Okay, so you can have as many independent variables you wish to have. So what we essentially are trying to find here is that we want to find an equation which will help us in finding out the weight of an individual given his height and age. So that's one thing. So that's one thing that we are trying to find here. The second thing that we are trying to find here is that how is weight related to height of an individual, and how is weight of an individual related to the age of the individual. So for instance, if somebody says if I increase my if my age increases by 1 year, how is going to affect my weight? So that question also can be answered from this particular equation. So let's run this particular syntax, particular set of codes, and we'll be able to get the estimates. Remember, we have got one independent variable, two independent variables in this case. So we'll be getting three estimates, two slope coefficients and one intercept. Alright, so when we run this, okay, it's not run properly, so let's run it again. Alright, so this is the output from your regression procedure, and this process is known as estimation. So we have estimated. There is an internal algorithm which is written in the background by SAS, which does this estimation. The algorithm that is being used in this case is known as the ordinary least square regression estimation. Okay, so the OLS, which stands for the ordinary least square regression, is the algorithm which is being used to find out the estimates, which are this intercept and the slope coefficients. So let's go one after the other. So we'll have so many things in the output. Not everything is very important, so we'll only see the important ones, which are very important before you finalize your model. The details about your model will be given first. You have got 22 observations and one observation is being deleted because it's a missing value, as I've already said in the beginning. Then we will have analysis of variance. In that, what is most important to see is whether the F statistic or the F value is significant or not. So what is significance? Significance is nothing but is just a concept which says that your value is greater than 0, or it has some impact, because if something is 0, it has no impact, right? If something is greater than or non-zero, so to say, it has some impact. Okay, so the probability value, so probability greater than F, should be less than 0.05 in order to say that the F value is significant enough. Okay, and what does that mean, and why is that important to be significant? It is very important to be it's important, and the first thing that you should see in a linear regression, because if it is significant, it says that the independent variables in the model combinedly impact or combinedly has effect on the dependent variable, or in technical words we say that the independent variables explain the variation in the dependent variable. Okay, or in more layman terms we can say that the independent variables are good enough and they are very helpful in predicting the value of dependent variable. Okay, so this is the explanation. If this particular value, F value, would not have been significant, then we should have simply stopped out there. There is no need to go further down in the regression output if your F value is not significant. So in that case, what should you do? You should ideally go back and add more independent variables or drop some of them, and do such exercises in order to ensure that the F value is significant enough. Alright, so the next step, so the next output which is very important to see is the R-square and the adjusted R-square values. Okay, R-square values explains the variation in the dependent variable. Okay, so dependent variable is weight. Okay, and the R-square value in this case is 74%, right? 0.74, so which is 74.23% precisely. So what it means that the two independent variables that we have used in the model are able to explain 74% of the variation in the dependent variable, which is weight, which is a fairly good value. Okay, the maximum it can take is 1 and the minimum it can take is 0. Although sometimes you can get a negative R-square, but it has no meaning, right? That's it actually means that your model is totally wrong. So R-square normally lies between 0 and 1, 1 being the highest, but normally you won't get an R-square value of 1. That means it explains 100% in the variation, 100% of variation happening in the dependent variable, which normally you won't find in a regression model. So the there is no thumb rule as to what is a good R-square value, but people say, and it differs across different area of study. There are some areas where even 0.2 is considered to be a good R-square. There are areas where 0.4 is considered to be a good R-square. 0.5 is also considered to be a good R-square value. Okay, and 0.7 is definitely considered as a good R-square value. The problem with R-square is that if you keep on increasing the number of independent variables, it is going to increase. Okay, but having a high number of independent variables, or a large number of independent variables, is not a good thing for the model, for a variety of reasons, because it is very difficult to explain. It's very difficult to implement or use that model in future, because there's just too many independent variables in place. So it's always good to have a minimum set of independent variables, which are the best set for the model. Okay, hence adjusted R-square is a slight variation of R-square, which can be explained in a similar way, the way we interpreted the R-square. So adjusted R-square is just a slight variation of R-square, wherein it penalizes the uses of independent variables. So the more number of independent variables that one would have, the more difference that you can see between the values of R-square and adjusted R-square. Okay, so that's a penalty that is levied on the model if it has got just too many independent variables. Okay, so normally people use adjusted R-square to be the indicator of a good model. Okay, so ensure you look at the adjusted R-square instead of looking at the R-square value. So 71% is the percentage of variation that is being explained by the model. Down below you will find the parameter estimates, and that's where we will be able to find out the intercept, the slope coefficients. We have got two independent variables, so we will be having three estimates, right? So we have got parameter estimates, right? We have got intercept, which is minus 181.35. The slope coefficient for height is 4.1. The slope coefficient for edge is 1.9, and we'll explain, we'll try to interpret what these values means, and how does one explain the model by taking these values. Okay, then right next to your parameter estimates, we have got standard error, we have got t values, and we have got p values. So the important thing to look at here is the p value. The p value, as we have already seen here at the very top, while explaining the significance of the F statistics, the p value explains the significance of a particular estimate. Okay, and it has to be less than 0.05 for the parameter to be significant. Okay, if you're not familiar with the theory of statistical significance, I highly recommend you to go through one of my video where I have explained what is statistical significance in great detail. You can also read about it in other sources. So what it essentially means is that the parameter estimate is not equal to 0. It's a non-zero value, and the moment we say the parameter estimate is non-zero, it means it does have some impact, or it does explain something about the dependent variable. And, or in other words, in layman terms, we can say that it is very useful. We can use it in the regression model. If it is not significant, what do we do? That is a question. Well, if it is not significant, then we just have to leave it there. We just have to remove that particular estimate from this equation. It cannot be used. It cannot be interpreted. We cannot interpret the parameter estimate if it is not significant. You can find out the significance by looking at t values or p values. They're essentially similar types. P value has to be greater than 2.7. I'm not sure the exact values, but it is, I think, greater than 2.7 or less than minus 2.7 to be significant. Or the best thing is just look at the p value. It has to be less than 0.05. 5. Okay, so this is significant. The intercept is significant, height is significant, the parameter estimate for height is significant, whereas the estimate for age is not significant because it's 0.3. It should be less than 0.05 to be called significant, but it's not significant. What should we do with age? Well, age will not be part of the regression model. We'll only have one variable and one estimate in this case. Okay, so we'll remove age from this equation. It's not significant, or it's not useful in this model. Or in other words, we can say that age does not explain the variation in weight, or we can say that somebody's weight doesn't get affected by his age. Now, one might think that is it intuitive in nature? Well, it is not. That is understandable. Age does matter somebody's weight, right? But after a certain age, the weight doesn't matter, right? Once you are an adult, your increase in age doesn't really affect your weight much. But in the childhood days, it does matter. If in your population most of the data points or most of the individuals are already adult, so you don't have people below 20 years or so. You don't have observation or individuals in your data set which are children, and so there is not clear mix of data with children and then adult data sets. They're all adult. So in that case, age doesn't really affect the weight of an individual. That's why it's coming out to be insignificant in this particular equations. Now we have the estimates in place. How does it help in having a final model in place? So we can write this equation as weight equal to the intercept plus 4.1 multiplied to height, and that's the linear regression for this. And once you have the linear equation in place, you can just plug in the value of height and you will find the corresponding weight. Okay, so what we essentially find out is that weight equal to minus 181.3 plus 4.1 into height, right? So given somebody's height, if somebody's height is given, you'll be able to find out his weight. So now this can be used for prediction purpose. You can predict somebody's weight based on his height by having this equation. Now this is just one use of linear regression model, which is prediction. There is another use of linear regression, which is known as inference. So I'll just write it down for you. So there are two things. One is prediction and the other one is inference. So the one that we have built here, weight equal to minus 181.3 plus 4.1 multiplied to height, can be used for both prediction and inference. Prediction is nothing but predicting the value of your dependent variable given your independent variable, whereas inference is trying to find out the relationship between variables. Now one would be interested in knowing that how is height related to weight in individuals or in the given data set. Now given the fact that height is a significant variable, now we have removed age from this equation. Remember why? Because it is insignificant. Now we can say that height is related to weight in positive way. Why it is in positive way? How can we say that it is related to weight in a positive way? Because the sign of the estimate is positive in this case. That means if the height increases, there is a high probability that the weight will also increase. So that is a positive relation or positive correlation to say. Alright. Another important thing you can also find out from this equation is a marginal effect. Okay, so there are three things you can actually find out from this equation: prediction, inference, and the marginal effect. So we know what is prediction, we know what is inference. Inference is just that you try to find out whether the dependent variable is related to independent variable significantly or not, and if significantly, whether in a negative way or in a positive way, right? Whether if the dependent variable, the independent variable increases, whether it has a negative impact or a positive impact. That you can find out from this linear regression model, and which is broadly known as inference. Marginal effect, on the other hand, tries to explain if there is an unit increase in the value of the independent variable, how much does that affect the dependent variable. So if you say, if I increase height by 1 unit, okay, if height is 10, your weight will be something, right? If height is, let's say, increased by somewhat some amount, what is going to be its impact on weight? Okay, so let's take an example and you will be able to understand. Okay, so if somebody's height, let's say, is 100 100 centimeter, I don't know whether I don't know the unit measure used in this case. All right, so let's take some hypothetical value. Maybe height is something like, let's say, is 100 60 unit, let's say. I don't know what is the unit is used here. So you multiply 60 to 4, which is 240, and then minus 180. Okay, so that comes out to be 59. Okay, so the weight of the individual is 59 if his height is 60 units. Okay, now what is the impact when we increase that to 61? Well, the impact is that when when we get the difference of the weight, you'll be able to find out the difference is nothing but 4.1. Okay, and that is the marginal impact or the marginal effect. Okay, if I take an example, that will be better. We can explain it better. Okay, so minus 181 plus 4.1 multiplied to 60, so that's the first one. And in the second one, you have got the same thing, minus 181 plus 4.1 multiplied to 61, right? So because we have increased the height by 1 unit, when you subtract the second minus the first, what you will be getting, sorry, this will be 4.1. okay, so what you will be getting is 4.1, right? Because this gets cancelled, so what remains is 4.1 multiplied to 60, 1 minus 60, which is 1. So 4.1 multiplied to 1 equal to 4.1. So the slope coefficient of an independent variable is the marginal impact of that particular variable on the dependent variable. Okay, so if you increase weight by 1 unit, the corresponding weight that will increase in the individual is 4.1 unit, and that's known as marginal effect. Okay, so these are the 3 things that we intend to find out through building a linear regression model. Now there are different aspects of linear regression model. In fact, I will go on talking about linear regression for number of hours. There are just so many things associated with linear regression, and it's not that simple. So just writing a reg data statement and defining your model is not enough while building a linear regression model. It's not that simple. There are so many issues one would find or one would come across while building such a model, and these issues has to be dealt with while building a model. It's not that simple, as I have said, and one has to get into the details of the issues related to a linear regression model, and there are variations of it also, in the sense that you probably have more number of variables, and the moment you have more number of independent variables, you will have problem dealing with them. Okay, and there are so many issues that one would come across while building a model with so many independent variables in place. So we'll see a few of them. It's not it's not possible to just have a look at all the problems that one will be facing. I'll just take 1 or 2 of them. Okay. One issue one would come across is that the problem of multicollinearity. Okay, so what is the problem of multicollinearity? Well, the independent variables that we are using may be very correlated with each other, right? Like height and age, they may be correlated with each other, and if you keep on adding more variables, there will be higher chances of correlation between one or a number of variables. That is a problem in linear regression. If the variables are highly correlated, then the standard deviation that you are getting in the model output will be not correct. Okay, and standard deviation is very important in an estimate because that gives you the confidence level, right? Okay. So if you go back to your model output, you have the standard error, right? Standard error uh, uh, is in somewhat, it just plus and minus, or it just it's like 4.1, right? So it's 4.1 plus 0.77 or 4.1 minus 0.77. It gives the confidence level, right? So that will be biased in case you have got highly correlated independent variable, and that problem is known as the problem of multicollinearity. So you have to identify this problem before finalizing a model. How do you do that? If you don't know, if you want to learn the theory of multicollinearity, you can watch one of my videos where I have explained the problem of multicollinearity, and I have explained how to detect it, how to remove multicollinearity in great detail. Okay, so one of the way in which we detect multicollinearity is through use of variance inflation factor. So we use the keyword VIF, which stands for variance inflation factor, which is very useful in terms of finding out whether or not there is presence of multicollinearity among the independent variables. In one of my video, I have explained in great detail what is variance inflation factor, how does it is calculated, and how does it is related to the problem of multicollinearity. Okay, you can watch that video. Alright, so if you use this option and build the model, you will get the corresponding value of VIF. Okay, let me run it again. The corresponding value of VIF, and through some threshold value, you will be able to know whether there is presence of multicollinearity or not. Now you can see the variance inflation factor wasn't there previously. Now it is there in your model output. So we have got the VIF for intercept, for height, and for age, right? The rule of thumb is that the VIF should be less than 5 for it to be for you to be confident about the fact that there is no multicollinearity. If it is greater than 5, then there is presence of multicollinearity. So that is the threshold people use. Okay, so VIF should be less than 5 for each independent variable, right? If VIF is greater than 5, then you have to do a more deep dive or more detailed analysis of independent variables, and if one or more variables are highly correlated, you just have to drop one of them, the less important variable from the model, right? So that's the way you can deal with VIF. So that's the way you can deal with the multicollinearity problem. Okay, you just have to drop some of the variables if there is presence of multicollinearity in a model. We don't have this issue in this case because it less than 5 in our case. All right, so this is one problem. The other problem that one would come across in linear regression, one is the problem of heteroscedasticity and the problem of autocorrelation. I'm not going to talk about these problems. They're a little more complicated, and I'll take these problems in a separate video, in another video. In fact, in some of my videos, I have explained about these problems in great detail. You can go through these videos. I'm going to show you another aspect of linear regression in SAS. So you can save the model output in your database. Okay, so for that you just have to use the keyword outtest and just provide the name of a dataset wherein you have you want to save your dataset or save your model output, so that you can use the model output in future, right, for finding out the future weight of individuals given their height, right? So that's the way you're going to do it. Okay, so you use the out test values wherein you want to save your model output in some kind of a data set. Alright, now we'll be using the third independent variable that we saw in the data set in the beginning, that is sex. So we've got two categories, male and female. So we might want to have separate models. So we might want to have separate models with respect to gender. One, as we have said in the beginning, if there is a great difference in the percentage of presence of male and female population, it's always good to have two models instead of just one. So in that case, you use the by statement. Okay, so you just use the by statement and he is going to give you multiple, two models. Or it can have more than two also if your variable or the categorical variable that you are using the by statement has more than two categories, right? Also, you can have multiple linear regression equation in the same statement. You don't have to write as another model statement in order to test multiple linear regression model. Let's say you want to have weight, height, height and age in one model and only height in the second model. You just have to write the keywords equation 1 and equation 2 and then define the model, and it's going to take care of both the models. So in this particular statement, we are seeing two things. First thing, we're going to have two models with respect to sex. So we'll have one model for male and one model for female, and we're also testing, or we are also estimating two models in just one sex statement. Okay, so there are two things we are trying to do here. Is there some error? Okay, so it says that it's not sorted. So what you need to do is that every time you're using a by statement, make sure that you are sorting the data set before using it in the regression. So you just use proc sort and then that will be sorted. So just sort the data with respect to sex. Okay, perfect. Now we will run this and then should not be as nice. Alright, now in the output you can see that you have separate models for male and female. You can see equation 1, because we have got two equations binded. So equation 1 and then sex here is female. So we have got 16 observation in the female population. So using that many number of observations, that is the model has been built. Okay, in the next output you can see the equation 2 has been built. In the population, sex is equal to female. Okay, then equation 1 with sex is equal to male, and then equation 2 with sex is equal to male. Right, so in total you have four equations, four models, right? Model 1 male, model 1 female, and then model 2 male, model 2 female, right? So you can test, or you can build several models in just one equation. So this is just one feature of SAS that I was trying to show here. Alright, now is it all fine, or do we have to do more about linear regression? Every time we build a linear regression, you cannot finalize a model without doing some kind of a validation. So validation is also known as testing your or diagnose your model. Okay, so you have several diagnostic statistics in order to ensure that your model is sound enough or good enough. There are various ways you can do it. Okay, if I've gone through some of my other videos, you might have come across cases where I have training sample, validation sample, and then building the model in training sample, validating in in the validation sample, and so on. You might have come across cases like bootstrapping or resampling techniques, I'm not going to use any of these techniques in this particular equation. This is the simplest of the model that I'm showing here. I'm not going to give you more complicated way of validating models. So what you can do in validating a model to ensure that your model is sound enough is that you just have to plot some of the test statistics and see if they're good enough. Okay, so for that we'll use the ODS statement, ODS graphics on, and below that we have just written ODS graphics off. So when you run your regression with ODS graphics on, you will get so many plots which will help us validating the model. So let's see them. Things not run properly. All right, now you can see the plots, right? Several of them. You can get the residual plots. Okay, so if you're familiar with linear regression theory, you must know that the residuals or the error terms in the linear regression should be random in nature. There should not be any pattern in the error terms. If you plot the error term with respect to the dependent variable, then it should be completely random, right? And there should not be any pattern, and they should be very close by, or they should be uniformly distributed across the negative side of the x-axis and the positive side of the x-axis, right? So that's the residual plot you can see here. Now you can see in our case there is no pattern. We can see that the error terms are pretty random in nature. There is no pattern. If there would have been some pattern, then there is something wrong with our model. You may have to revisit your model. You may have to ensure that your your diagnosis of the model in terms of finding out multicollinearity, autocorrelation, heteroscedasticity are well dealt with before finalizing model. So that's very important. In our case, that's not an issue, except just one issue. You can see an outlier in this case, right? So this is just an outlier. It should have been removed before we build the model. But this is one case that should not make a lot of impact. But you may want to, and it's always advisable to do so, you may want to go back and remove that variable and run the regression again and see if there is a significant impact in the estimate. If there is a significant impact, then you should remove this particular observation from your data. So that's an outlier. So you can find out some of the outliers from residual plot and just remove them. Except that we see no pattern in the residuals, and it's all randomly distributed, and it's distributed in both sides of the x-axis. So that's fine, perfectly okay. So there's no issue with that. Another important thing we might want to see here is whether the error term is normally distributed or not, right? So we might have come across the assumption in linear regressions. One of the assumption is that the residual should be normally distributed, right? And you can see the residual is somewhat normally distributed, so that looks normally distributed. If you remove this outlier, I'm sure it will be even very closer to normal distribution. So that is that will be very good then. Okay, so these are some of the diagnostic statistics that you should look at before finalizing the model or before signing off. Okay, so as I've said, these are the steps one has to perform. These are the basic steps. Even I would even say there are more steps to be followed for building a model, but these are the bare minimum steps one has to follow in building a linear regression model. Linear regression model can be used for several purposes. As I've said, it can be used for prediction purpose, for inference purpose, and for knowing the marginal effect of independent variables on the dependent variable. This model can be used for prediction of values for dependent variable and for policy making purpose, through finding out the relationship between variables and through finding out marginal impact on the dependent variable. Okay, so that's all for this particular session, and in the next session we'll learn more about the more aspects of linear regression through autocorrelation, heteroscedasticity, and we'll also see how we can use sampling techniques to validate models. So see you in the next